Hi friends, this is Pankaj Goyal. On behalf of the Impulse Group, I have made this video regarding PWM technique. Before proceeding further, I would like to read one question which is asked in GATE 2015. This question says, the single phase full bridge voltage source inverter shown in this figure had an output frequency of 50 Hz and it uses the unipolar pulse width modulation with switching frequency of 50 Hz and the modulation index of 0.7. For input voltage, this is the DC input voltage for this voltage source inverter is given as 100 volt DC, and the value of LCR in this circuit is given like this. Now we need to find the amplitude of the fundamental component in the output voltage of this V0 under steady state condition. Here there are some few terms you should know. One is basically unipolar PWM, second is what switching frequency, third is what modulation index. What are basically unipolar PWM, modulation index and switching frequency we will discuss in this video, and finally the amplitude of this component in the output voltage of V0 under steady state condition. In this figure, a typical diagram of a full phase bridge inverter is shown in this here. This is the input voltage DC VD. It is assumed to be constant, and we are taking the output between these 2 points. This is A and B, which is given as like this: V0 equals to VA0 minus VB0. How this is calculated? We can take a loop from this point to this A to O, then O to B, and then this loop. We can consider this loop. If we move from here A to O, VA0, and then from O to this point B, plus of VOB, voltage of this, and after then this point to this point, this B to this is equals to minus V0 equals to 0 in this loop. So we can write here V0 equals to VA0 plus VOB, and so we can write here VBO, because this voltage equals to this VBO equals to minus VOB. So here if we talk about particularly for the PWM inverter, then the input voltage should be essentially constant in magnitude, and what we need here, we should be able to control the magnitude as well as frequency of output voltage. This should be our prime requirement. Now how to achieve this? This is achieved by the pulse width modulation of this inverter switches. That is why we call this particular inverter as a PWM inverter. There are various schemes by which we can pulse width modulate this inverter switches, but if we get output shape as near as sinusoidal voltage, then this particular scheme is called the SPWM technique. So for this we need to generate some switching signal that is applied to these inverter switches, so that we can get the output as near as sinusoidal voltage, and the frequency we can get output voltage as a desired frequency. For this we need to generate the switching signal. to generate this switching signal, we require two signal. One is basically called the control signal or reference signal, and second is the carrier signal, which is generally taken as triangular signal. The control signal reference signal in case of SPWM technique is taken as the sinusoidal signal, whose frequency is considered, let us suppose, f1, and the carrier signal, which is generally triangular signal, which is having a constant amplitude, and assume the frequency of this is fs. So already said that we will keep constant the amplitude of this carrier wave, and we can change the amplitude of our reference wave, that is sinusoidal wave. So by varying this amplitude, we will control the duty ratio, that is called the switch duty ratio of these switches. And after that, by varying this switch duty ratio, we can control the output at a desired frequency, and we can get our output as per our requirement. Now my question is, what should be the inverter switching frequency? Inverter switching frequency is the frequency over which these inverter switches are operated. They are making on and off according to the switching instances. So which signal is responsible for this, whether a control signal or this carrier signal? The control signal frequency is generally taken as the frequency which we require the fundamental component of this output voltage, and the carrier frequency is taken as fs, which is actually responsible for this switching of these inverter switches. So inverter switches frequency is the same as the carrier frequency, and this carrier frequency generally we kept constant for a particular inverter fs with its amplitude as V3RI constant. So this frequency fs is called as triangular waveform frequency or switching frequency or carrier frequency. Now what is the role of this control signal? This control signal is used to modulate the switch duty ratio, and it has a frequency f1. This frequency f1 is also called the modulating frequency, and this frequency is same as the desirable fundamental frequency of this inverter output. And after this output voltage will not be perfect sine wave, and it will contain some voltage component of harmonics, voltage component at harmonics frequencies of f1. Now I introduce the term amplitude modulation. Now amplitude modulation is given by the peak amplitude of this reference signal and the peak amplitude of this carrier signal. Here this switches TA plus, TA minus and TB plus and TB minus are controlled based upon the comparison of this V control and V triangular, and the output voltage, this VA0 and VB0, does not depend upon this direction of this current, only depend upon the comparison of this V control and V triangular. Before proceeding further, I would like to know what happens is this TA plus is on. When this TA plus will be on, then this will be, we have a short circuit. So what happened to this voltage VA0? This VA0, this when TA plus is on, then this VA0 KVL in this loop, VA naught minus of VD by 2, this must be equals to 0, so this VA naught will be equals to VD by 2. Similarly, what happen when this is on and this is off? So under this condition, this will be have as a short circuit by using this KVL in this loop. So we will be having VA naught plus VD by 2, this must be equals to 0, so we get VA naught, this must be equals to minus VD by 2 when TA minus is on. Similarly, we can get here, if TB plus is on and this is off, we will get VBO as equals to VD by 2, and if this TB minus is on and TB plus is off, we will get VBO, this is equals to minus of VD by 2. We can calculate by using KVL in the corresponding loop. Now my question is that how this switching for this inverter are created. For this I have already said that we are taking control signal as a sine signal and the carrier signal as a triangular wave. Here the amplitude of this triangular wave is V TRI is this, and amplitude of this control signal is this. This is basically the amplitude of control signal is V control. So here we can say that MA is equals to V control by V TRI, so it is actually less than 1. So under this condition my modulation amplitude modulation index is less than 1. Okay, I have made a scheme for that. If my voltage of this control signal is more than this triangular, then my corresponding TA plus will be on. Okay, and if I make this carrier wave voltage is more than this control voltage, under this condition I have made that this TA minus is on. I have made the switching something like that, and in the previous diagram we can see here, if this TA plus is on, so to get the output voltage this TB minus must be on, and if this TA minus is on, then here TB plus should be on. Okay, so if this TA plus is on, then TB minus should on with this, and if his TA minus is on, under that condition this TB plus should be on. Okay, now when TA plus is on and along with this TB minus is on, then we'll get output voltage in this loop. Considering this loop TB on is this, and this loop, then we get output voltage this in this loop minus VD naught minus VD plus V naught, this must be equal to 0, so we get output voltage as plus VD. So when my reference signal is more than my carrier signal, under this condition this TA plus and TB minus will be on, and the output voltage, corresponding output voltage will be V naught equals to plus VD. What happened to the case when TB plus is on and TA minus is on? This TB plus is on and this TA minus is on. So what will be the value of this V naught? We will take this as a loop, so by using here this is minus VD and minus V naught, this must be equals to 0. We will use KVL equation in this loop, so we will get V naught equals to minus VD. When my under this condition this amplitude of carrier is more than this reference signal, under this condition TA minus and TB plus will be on, and the output will be minus Vd. When this reference voltage is more than the carrier voltage, under this condition Ta plus and Tb minus is on, and V naught output voltage will be plus Vd, and the corresponding output voltage is shown in this figure like this. So in this case my output voltage is switching between this plus Vd and this minus Vd. So this scheme of PWM technique is called bipolar PWM technique. Okay. Now consider different case when we are taking two reference signal. One is V control, second is minus V control. This is 180 degree shift of this V control. This is V control, and another one is this is minus V control. This is minus V control. We are taking two reference signals in this case, and this is the triangular. What is the switching scheme in this case? Here we have taken, if this V control is more than V triangle, then Ta plus should be on, and Va, and under this condition will be Vd. How it is, we will see. What we have said, if this V control is more than V triangle, then Ta plus will be on, and this Van should be equals to Vd. What is this neutral point? And is this neutral point? This is the negative bus voltage, DC bus voltage. So if this Ta plus is on, definitely we will, this is Van. In this loop we can get here this minus of Vd plus Van, this must be equal to 0. So Van should be equals to plus Vd. So for this case where this V control is more than V triangle, under that condition Van must be equals to Vd. What happen when this V triangular is more than this V control? When this V triangular is more than V control, under this condition we want that our Ta minus should be on. What happen when Ta minus is on? When this Ta minus is on, under that condition Van should be equals to 0. The same can be seen here. Then if V triangular is more than this V control, then Van is 0. What about this Vbn? Similarly, if this control signal, if this minus V control is more than V triangular, then this Tb plus should be on, and for opposite case, if minus V control is greater than V triangular, then this Tb minus should be on. Now we will see what happen if Tb plus is on, and what happen if Tb minus is on. If this Tb plus is on, under that condition we will get this Vbn here in this loop. In this loop we will use this KVL, so we will get here minus Vd plus of Vb, this must be equals to 0, so we will get Vbn, this must be equals to plus of Vd. If what happen if this Tb minus is on and this is off, under this condition this Vbn should be equals to 0. Vbn should be equals to 0. So the same can be seen here. If this V control minus V control is more than this triangular, under that condition we are getting Vbn is as plus Vd, otherwise it is 0. From the previous figure we can see here this output voltage V naught is VA naught minus of VB naught. So the output voltage which we get by subtracting this minus this, we'll get V naught. It will be something like this. It will be something like this. So when switching occur, the output voltage V naught changes between 0 and VD or between 0 and minus VD. So because of this switching, for the first half cycle it is unipole, for the second it is again unipole. So this switching is called unipolar voltage switching. This switching is called unipolar voltage switching. While in the previous section we have seen that for half cycle we are getting positive voltage as well as negative voltage. That is why it is called bipolar voltage switching. Now see this dashes line. What is this dashes line? This is actually the fundamental component of output voltage. Fundamental component of output voltage. We can see here this amplitude. This amplitude is nothing but the average taken of all these positive and negative halves. For this is actually positive, for this actually it is negative. So overall we will see that the amplitude, this amplitude depend upon what? This positive and negative area. Now my question is, this amplitude dependent upon what other parameters? Does it anything to do with this MA? Here I have considered this plus amplitude modulation index is less than 1. Does this amplitude, the amplitude of this fundamental voltage wave has any dependency with this modulation index? We will see now. See this figure. Under this we have actually keep on changing. This is the control signal, this is the triangular signal, carrier signal. In first we have kept this amplitude of this control signal is this one. In the second we have kept this amplitude of this control signal is this one, and in third case we have kept the amplitude of control signal is this one. We are keep on increasing the amplitude of control signal. It means we are keep on increasing the value of amplitude modulation index. What happened to the output? Let us suppose we are taking the case here for the bipolar technique, bipolar voltage switching. So if this is basically what? Control signal, this is triangular signal. If this control signal is more than the triangular signal, then my output voltage will be plus VD, and under this condition, this triangular voltage is more than this control signal, my output voltage will be minus VD. So in this cycle it will keep on increasing the amplitude of this control signal, then will keep on increasing this plus VD is keep on increasing, and on the same time this minus VD is keep on reducing. In this case plus VD is from here to here, this one. In the second case this plus VD will be from this point to this point, and in the third case will be less than the previous one. Okay, so what happened whenever I am increasing the peak of this control signal, means if I am increasing this modulation index, it means my plus VD area is keep on increasing and this minus VD area keep on decreasing, so that my fundamental output voltage peak keep on changing depending upon the value of this amplitude modulation index. So my let us suppose this V naught is the output. So
So my V naught fundamental component is obviously we have shown here. This is sinusoidal dashes line in the previous slide. So this V naught depend upon what? This MA. This actually dependent upon the this amplitude modulation index. Okay. So and on the same time it also depend upon this plus VD minus VD, so it is also dependent upon this VD. So definitely this is fundamental component, so we are giving here sin of omega 1 t because of this fundamental component. So this my output voltage, fundamental component of output voltage depend upon this modulation index, the input DC voltage and the frequency, and the peak of this can be given as this must be equals to MA into of this VD, and the same is also valid for unipolar voltage switching. So when I have whatever I have considered here, this MA is less than 1, it means I am talking about under modulation. Under modulation condition, this my fundamental component output voltage depend upon modulation index and the input DC voltage. So the peak amplitude will be equals to V naught will be equals to MA into of VD. Now assume a condition when I am keep on increasing the value of this amplitude, keep on increasing the value of this amplitude, that is the my reference signal. So assume a case where this is something is the case when my amplitude of this reference voltage become more than this triangular voltage. Under this condition my MA will be greater than 1. This is the case called over modulation. Under over modulation case, what happened? There are some particular points where there is no interaction in between this carrier wave and this reference wave. So under this condition, if we apply our concept like if the V control is greater than V reference, we should get output voltages plus VD, assuming this bipolar voltage switching. So here there is no, because of this no interaction, we will get always this plus VD. So under this condition, this linearity concept, previously we have seen that this V fundamental output component is proportionally to MA, proportional to MA, but in this case, because of this non-interaction case, this non-linearity does not hold good, does not valid. Consider a case when my reference voltage becomes so large, there is no interaction in this positive half cycle and in this negative half cycle. So by applying this concept, we will get what? We will get output voltages continuously plus VD all the time, and under this condition we will get minus VD all the time. So what we get here in this case, output voltage will be a kind of square wave. Whenever we get output voltage as square wave, so that we can say here that under this condition output voltage, fundamental component output voltage will be equals to 4 Vs by pi into sine of omega 1 t. So under this condition, amplitude 4 Vs is nothing but our input DC voltage, that is VD. So under this condition, amplitude of fundamental component will be equals to 4 VD by of pi. So if M modulation index is less than 1, then this output voltage dependent upon this modulation index. But if it is the case of over modulation, then the peak amplitude of fundamental voltage does not depend upon this over does not depend upon this modulation index. So in this figure we can see here, if our modulation index is less than 1, then the output voltage, this is actually the peak of the fundamental component of output voltage, that is actually dependent upon this, linearly dependent upon this amplitude modulation index. And this is the case of over modulation, when this MA is more than the unity. So this is over modulation case, and when my amplitude modulation index become very large, near about 3.25 or more than that, is a particular case of I am taking here, then we got this square wave region. Square wave region is nothing but we are getting as output is a square wave. This is basically a square wave. So we can say that the square wave inverter is nothing but a special case of SPWM, when my modulation index is very greater than 1, it is very large. So we can reach to a conclusion that if my modulation index is less than 1, under this condition the peak of this output fundamental component of output voltage will be dependent upon this modulation index. If over modulation case, under this condition this maximum can go up towards 4 Vd by pi from Vd, because if MA is greater than 1, then this will be equals to Vd. So if my modulation index is more than amplitude modulation index is more than 1, then my fundamental component of output voltage amplitude will be between Vd to 4 Vd by pi. So by keeping all the concept in mind, now we can able to solve this question. Here unipolar PWM case is taken and the modulation index is given 0.7. If modulation index is 0.7, it means it is less than 1. So it is the case of under modulation. So under this condition, our output voltage, output of this full phase VSI is peak, its fundamental peak will be proportional to MA and will be equals to MA into of this DC voltage. This is actually the peak. The peak will be equals to fundamental. The peak fundamental frequency component of this output voltage will be equals to MA into of V in. If we get to know this amplitude of this fundamental component of this voltage, this is equals to 0.7 into a V in, that is equals to 70 volt. If we know this amplitude, we can calculate by using simple KVL KCL rule, and we can get this amplitude. Here important thing, this omega into L, so this omega is used to be this 50 Hz frequency, and here this is 1 by omega C. So under this condition, frequency has to be used this fundamental frequency, that is 58 frequency, because switching frequency nothing to do has with this. It is only used for the switching of the inverter switch which we have used in this full phase inverter. Thank you. And in the same way, the question which is asked in 2016, we can solve it by using the same concept.